Alright, silly people, here's the situation. Um, we're in the particle in a box, and we are trying to prove that the energy is always positive um, for the particle in the box. So uh, E is greater than 0. For this proof, um, suppose that we set E to 0, for example. And we're going to show that this equation kind of falls apart when we do that. Remember, for the particle in the box, we have to have these boundary conditions that the wave function at 0, x equals 0, and at x equals a are both equal to 0. And that's where the contradictions are going to pop up. So if e is 0, then the Schrodinger equation is looking like this. We have minus h bar squared over 2m. We got the second derivative of the wave function, del x squared equals to 0. And then for brevity, I'm going to let that 0 gobble up the h bar stuff. So it's that. You can integrate this pretty naively. The first integral of 0 is a constant. I'm going to call it a. Then the integral of that will be ax plus b. But the problem arises whenever we plug in our boundary conditions. So if we look first at x equals to 0 and plug this into our wave function, we have that it's just b. And we know that this has to equal 0, so we found that b is equal to 0. Cool. So our wave function is now just looking like ax. If we plug in a for x, which we also know should be equal to 0, we get a little a equals 0. Now we know that little a is not 0 because it's a variable defined in the problem. And so to solve this, we find that a is equal to 0. So we have that psi equals to 0. Awesome. There's no solution here besides the trivial one. There's no wave function for negative or 0 energies. But now we're going to consider negative energies. So suppose now that we have E is equal to minus epsilon, where epsilon is some positive constant that I'm just defining for fun. Then our Schrodinger equation is looking like minus h bar squared over 2m del squared psi del x squared is equal to minus epsilon psi. And we'll let the minus signs cancel each other out, and I'll also move this stuff to the other side. So I'll have del squared psi del x squared equals 2m epsilon over h bar squared times psi. And I'm going to define 2m epsilon over h bar squared to be some constant k squared, so that our differential equation actually is now identical to the Helmholtz equation in first dimension, which famously has solution a e to the kx plus b e to the minus kx, where a and b will be determined with boundary conditions. So we can check our boundary conditions on this thing. So we have that the psi of 0 will be 0. So we have that a, each of the 0 is just 1. So a plus b equals 0. Let's leave that for now. I'll come back to that later. Let's also check psi at a, which will be e to the ka plus b e to the minus ka. That'll also have to be equal to 0. For this equation, I'm going to multiply both sides by a factor of e to the ka, so we'll have e to the 2 ka plus, um, it's just now b on this side, and this whole thing is equal to 0. And then we can use the first equation that we got from the first boundary condition to say that b is equal to minus a, right? So we have that a e to the 2ka equals a, and you can let the a's cancel each other out now. And you have e to the 2ka equals 1, which a is a variable that is defined in the problem. K is a variable that we came up with. So k is the thing that's going to have to go to 0 for this to equal 1. But remember, k is just the square root of 2m e over h bar squared. M better be positive, otherwise it's a particle without mass. And those don't exist. I'm just kidding. But also, we defined epsilon to be positive to solve for this stuff. And so the only thing in here that we can set to 0 is epsilon, which is a contradiction to our thing. So there's no solution here either. So if you're doing particle in the box, you better find that your energy is positive, or else weird things happen. Okay.